So the next talk is a multi-attribute-based predicate encryption from some assumptions by David Point-Chaval and Robert Sadlich, and Robert will give the talk.
So hi everyone, this is a joint work with my PhD supervisor David, and this talk is about attribute-based encryption, which is a special case of the previous talk where the encryptor encrypts the message mu with respect to some additional attribute x, and keys are generated with respect to a policy f, and decryption reveals the entire message mu if f of x is 1, and otherwise we learn nothing. And this primitive comes in two flavors. When we talk about attribute-based encryption, we mean that the ciphertext can leak the attribute x. Otherwise, if we want stronger security where also the x is hidden, then we want predicate encryption. And here we consider an extension called multi-input ABE, so this is somewhat orthogonal to the previous talk, where there we had a single encryptor and we distributed the key generation. Here we do the opposite. We have centralized key generation, but we have n encryptors, each encrypt their own message mu I under some attribute xi. And a joint decryption of n ciphertext is possible if the tuple of all attributes satisfied in policy n that now also, the policy f that now also has arity n. So either we learn all or messages or none. There is no partial decryption. And so the new primitive in this work is multi-client ABE, where we have two new features compared to multi-input ABE. First, we separate the encryption keys, a different one for each encryptor. This allows to consider a stronger security notion, where we corrupt a subset of these keys, and then we still want a meaningful notion of security, whereas in the multi-input model, all security is lost. And the second new feature is encryption with respect to labels. And decryption is only possible if all ciphertexts are generated with respect to the same label. Otherwise, we learn nothing. And a small technical note, so without loss of generalities, it's sufficient to consider only one message encryptor. The others can just encrypt an empty message. This is because we can generically upgrade from a one message to an n message scheme by just considering n instances and then rotating the slots. Now about the state of the art. So previous to this work we noticed that all existing constructions fall into one out of two categories. Either we can deal with strong policies and also need strong assumptions for the security proof, or we can prove security from nice assumptions, but then the policies have some weakness, or so they are not weak, but they have some limitation, which is they can be viewed as a conjunction. And this means that essentially we evaluate an independent predicate in each slot, and then globally we only can consider the conjunction of all of them. And we therefore ask the question if it is possible to build multi-client ABE from standard assumptions for global policies, meaning not a conjunction. And the answer is yes, but there are some limitations that correspond to the following known implication, which says that if we have multi-input ABE for a polynomial arity and all NC1 policies, then we immediately get witness encryption. And witness encryption from standard assumption is an open problem. And what we try in this work is to somehow lower the gap between existing multi-input ABE schemes and this powerful variant that we would need to get witness encryption. And specifically, we identify three different cases. The first one is, let's see what happens if we lower the bar for the policies, and indeed we can build multi-client ABE for all NC1 policy, 0 policies, and a bunch of other policies like threshold policies where the threshold is either constant or everything minus a constant. And the second part is here we relax the arity condition to some logarithm, Specifically, we want that the total number of attributes is just logarithmic in the security parameter. And in this case, we can get multi-client ABE for all NC1 circuits. And the third case is here we relax the security model for MCABE, such that we do not imply multi-input ABE anymore, and therefore we also lose the implications to witness encryption. And in this case, we can build MCABE for all NC1 circuits and also for polynomiality. And the second part of the talk or the second part of the paper is dedicated to the construction of multi-client predicate encryption, where we digitally want to hide the attribute. And so far there are two existing constructions, one from RWE for conjunctions of bounded depth circuits. The issue here is that we are not secure under collusions. And the second existing construction is a compiler from multi-input ABE to multi-input predicate encryption. The problem here is that this works only for arity2. And we essentially generalize this compiler from arity2 to any constant arity, and additionally we lift it from the multi-input to the multi-client setting by adding corruptions and labels. Now, so the remaining time I would like to use to talk a bit about our multi-client ABE construction. And our starting point is a framework from to build a single client ABE. Here we combine in a product functional encryption and linear secret sharing schemes. And specifically the idea is, so in our case we want to build key policy ABE, which means we embed the linear secret sharing scheme in the IPFE keys. And for the ciphertext we sample some randomness R and encrypt it such that IPFE decryption gives randomized versions of these linear secret sharing schemes, which can be used to make the security proof work. Now the big question here is, how do we turn this into a multi-client ABE scheme? What we need to do for this is we somehow need to decentralize the generation of the ciphertexts. And unfortunately, the structure of this ciphertext is not very decentralization friendly, because so the issue is that we have a bunch of IPFE ciphertexts that correspond to different attributes from different slots, but all of them encrypt the same randomness R. And it's not quite clear how to decentralize the generation of these Rs. And indeed, in our construction, we do not even try to do that. We just let the first client do all the work and generate all the IPFE ciphertexts, and then we add a mechanism on top to still let the other clients control which of these IPFE ciphertexts can be learned by the decryptor. And so more specifically, we add a second layer of encryption, identity-based encryption, where the identities are the labels and the attributes under which we encrypt. And then the other clients are responsible for the generation of the IBE decryption keys, and depending on which keys they provide, they can essentially control which of the IPFE ciphertexts are revealed, even if all IPFE ciphertexts are generated by the first client. And so I guess this looks already a bit better, but there is still one fundamental problem here, which is that, how do I get the pointer? So we can see that currently the ciphertext of the first client still depends on x2 through xn, which are the attribute inputs to the other clients. And I mean, the whole point of multi-client ABE is that we do not have all the clients given as input at the same time. And so this does not really work. And what we need to do instead is that the first client essentially needs to consider all possible combinations of attributes x2 through xn that are given as input to the other clients. And if we do this in a very naive way, then meaning we just iterate through all possible combinations of policies, then this set here grows exponentially, which requires us to restrict the number of attributes in the scheme to some logarithm. And if we want to do better, meaning we would like to have a constant number, we want to have a polynomial number of slots in the scheme. In this case, we somehow need to reduce the growth of this set from exponential to some polynomial. And so we don't know how to do this for all of NC1, because in this case we would get witness encryption, which seems to be the sort of barrier that I mentioned earlier. But we know how to do it for certain simpler policies like NC0, because they have the very nice property that even though they take a polynomial number of inputs, actually they depend only on a constant size subset. And so long story short, this observation allows us to see that even though we have an exponential number of combination here, most of them are somehow equivalent or redundant because they wouldn't change the output of the policy anyway. And in this way, we can reduce the size of the set from exponential to some polynomial, which is exactly what we need to reduce the size of the set and make the whole construction efficient. And the argument for other policy classes, like threshold policies, are essentially the same. Okay, so let me conclude briefly. In this work, we initiate a study of two new primitives that we call multi-client attribute-based encryption and multi-client predicate encryption. And we give new constructions for multi-client ABE for global policies, meaning they cannot be viewed as a conjunction. And this was previously unknown from standard assumptions, even in the simpler multi-input ABE model. And additionally, we give a new generic compiler from multi-client ABE to predicate encryption for a constant number of slots. And this was previously unknown as well. That's what I wanted to say. Thank you very much, and that's it.